So SELinux, this is one of those wonderful things that we have to deal with when we are putting together Android platforms. And although we know, of course, SELinux is good and is making our systems more secure, it doesn't make it any less annoying. So I've got a couple of tips and tricks, and again, I'll be happy to, if anybody has any of their experiences, let me know. But I want to talk about these tools: SESearch, SEPolicy check, and also an issue I had the other day where I had to decode an INO number to track down an actual file. And this is based on, or some of the examples at least are based on the policy for a simple little web server, which anybody who's done my training class will recognize. This is one of the sample implementations we have. So it's a little HTTP daemon. This is the TE file for the daemon. And there are some allow rules to allow the daemon to access something called a HTTP data file, and also to be able to do things with sockets. So it can bind, it can do node binds and main binds, and yeah, other stuff. So that's the policy for the daemon, and then here is the file contexts. So we are labeling. Actually, the daemon in this case is BusyBox. We're just using BusyBox in a very simple way. So we're labeling BusyBox as being a HTTPD exec, and we're labeling the directory that contains the HTML files, which is happens to be in vendor etc. We're labeling those as HTTP data files. So first of all, you can see all this stuff at runtime. With the -z option to PS, we can see that the BusyBox executable has been labeled with the context HTTPD, so it is indeed a HTTP daemon. And we can also see the results of the file contexts. So we can see that we have labeled vendor bin BusyBox. That's now is a HTTPD exec. And if we look in the HTML directory, we can see that there's a HTML file there, and that's been labeled as a HTTPD data file. So first of all, then, I want to have a look at using SESearch to, first of all, retrieve this information. So you may not have these source files available when you're doing the diagnosis. So SESearch allows us to take essentially the binary policy file and retrieve the rules from that. And also it allows us to query it in various ways to see how these rules kind of coalesce and combine. The basic usage is like this. So you have SESearch, then you specify the rule that you want to search on. So this can be an allow rule or a don't audit or never allow. There's a few others as well, which I haven't included here for clarity. Then you can give the source context, so that would be the program. The target context, that would be the thing that you're trying to access, typically a file or a socket or something. You can give a class, and you can even give a list of permissions. And you can give some or all of these parameters, you don't have to give them all. So I've been kind of fiddling around with SESearch for a little while, and that's why I'm documenting it here. The first thing that is likely to set you off in the wrong direction is there is a copy of SESearch in AOSP in this directory here, but it's an old version and it doesn't work. So somebody should actually delete it, I think. It doesn't work mostly because it uses the old 2.7 version of Python rather than the later one. So forget that. You need to install a fresh copy of SE Tools. This would be using the SE Debugging package, the SE Tools Debugging package. And then we can do things like this. So we need, first of all, to get a copy of the policy file that we're going to be diagnosing. And we can do this with an ADB pull. Then we can use SESearch. Notice I'm using user bin to give the absolute path, so I don't use the SESearch from AOSP. And in this case, I'm looking for allow rules for HTTPD to see which rules apply when it's accessing HTTP data files. So that's the query, and we're passing it the policy we just pulled in from here. And we get these lines, we get these options. So some of these we recognize. So lines 4 and 5, these are directly from the TE file earlier on. And just go back a tiny bit. Yes, there are these two allow rules here for which allow HTTP data file, so allow HTTPD to search a directory labeled as HTTP data file, and also to open and read files likewise. So that's those two lines here, 4 and 5. But there's also a bunch of other stuff, which is maybe a little bit surprising. So there's another rule here which says that HTTPD, sorry, that says that domain can do a get after open read on a symbolic link that's labeled as being a vendor file type. And also down here, there are other rules which imply that it can do other things with vendor file types. So this comes about because the types that I'm using, HTTPD and HTTP data file, they are all based on other types. And so they inherit capabilities. So HTTPD is a type of daemon, type of domain. In fact, you can see that if we go back to here. First thing I say is type HTTPD is a type of domain. So HTTPD can also do the things that domain can do. Likewise, vendor file type. HTTPD data file is a type of vendor file type. So because there are rules elsewhere that say that essentially domain can access these vendor file types, we can also do various other things on directories as well. Okay, so what are we doing here then? SESearch is giving us the complete list of allow rules which allow HTTPD to access a HTTPD data file. You may want to say, well, okay, what else can HTTPD do? We can do this. We just do essentially the same query as before, but we don't give a target type. So allow rule for source context HTTPD, and then just print out everything. This prints out an awful lot. I've printed the first few lines and the last few lines, but there are a total of 185 allow rules which can apply to a HTTPD. So it turns out it can do a lot more than you thought it could. And I can go into more than that, but those are just two, I think, useful examples. So the next two I want to look at is SEPolicy check. So SEPolicy check is something specific to AOSP, and you need to build it first of all, like this, and then you can use it like this. Now this is a pretty basic tool, but it does answer some questions that SESearch doesn't. So SEPolicy check, you give the source context, the target context, the class, the permission you're interested in, and the policy file. So once again, we call the policy file. Then I want to say, well, so HTTPD, can it read a HTTP data file? So we know it can because we explicitly put that into the TE file. So we run this check and it says match found. So good, that worked. So we can now say, well, but can it write to a HTTP data file? So same check, but with permission write. And now it doesn't return anything. Slightly annoyingly, it doesn't say no or anything useful like that. It just doesn't say anything. So if you see match found, that means yes. If it doesn't say anything at all, it means no. So SEPolicy check handy little tool for answering basic questions about who can access what. And then the third case is a little bit different, but this is playing hunt the inode. So the other day I had an ABC pop up like this. And so it says that simple service app is trying to access an object that is a system data file, which is a directory. And for the information about the thing it's trying to access, it just says name equals data, device equals DM8, and inode is 97. So I was stumped for a little while to work out what the hell this is. So bit by bit. So first of all, we need to decode the device. So this is the block device that the file system is mounted on. We need to find the mount point. The most concise way of doing this actually is to use the disk-free, the df command. And it's told us, so dev block DM8 actually is mounted as /data. So it's the data partition. That's useful to know. And now we need to find inode 97 in that partition. So we can use the find command with -inum, and it prints out the path. Actually prints out two paths. It prints out /data/data, and also /data/user/0, which is a symbolic link, in fact, to the first one. So I was quite pleased with this. So now I can say, well, the ABC is caused when simple service app tries to do a directory search on /data/data. I still don't fully know why it was trying to search that directory in the first place. It isn't in code I've written, and I haven't actually got around to checking that. But that's useful information. Finally, if I want to add an extra rule to fix this, this violation, I could do it in several ways. The lazy way is to use audit to allow as ever. So audit to allow, once again, we need the policy file, and then we just take everything from logcat, pipe it all to audit to allow, point it to this policy file we just got, and it says allow simple service app, system data file, directory search. So then I can copy and paste that into the TE file for this application, and ta-da, job is done. And that's it. So I thought, I hope that was useful. Like I say, these are things I've been fiddling around with for the last week or so. So I thought I'd put them together into a note, both so that I can remember them, and also maybe somebody else finds them useful. And that's that. Oh, I should say, does anybody have any questions?
Hello.
Hi. Yes. Hi.
Hello. Thank you for the this part. It was interesting, but I want to ask about how to deal with when you generate the SEPolicy through the tool audit to allow. Mm-hmm. Sometimes we get when we update the file context and the files .to to add the generated SEPolicy, we after the compiling we can have compiling errors like never allow. You cannot use this SEPolicy rules, like the domain or the labeling are filtered by the AOSP. How to deal with it?
Yeah, well, basically you can't. So the audit to allow program doesn't know anything about or doesn't check on any never allow rules. So just because it generates an allow rule doesn't mean to say it's actually going to work in practice.
Yeah, exactly.
Okay, go ahead.
Yeah. So because every time when we add or develop a new module and we integrate it in the code source, we have to add the SEPolicies and to work our model correctly in the enforcing mode. So audit allow, we cannot trust every time that the generated rules are correct.
Indeed, yes.
Yeah,
absolutely.
Yeah, but it's quick, as you mentioned, and lazy tool to perform and help us.
Exactly. So you can search for never allow rules using SE search with -- never allow. So you can use that to print out never allow rules associated with a particular thing. These never allow rules are defined in the SEPolicy. And they are there essentially put there by the Android developers to prevent us from doing things they don't want us to do. So you can, well, actually, first of all, Ahmed just pointed out, you can actually add SELinux ignore never allows to true. You can put that into your, I guess that's into your build config MK file. But obviously, you don't want to do that except in debug systems.
Yeah, of course.
But yes, so for production systems, you can't get around a never allow rule. If there's a never allow rule there, you're stuck. And you'll have to find some other way of fixing the problem.
Yeah. Understood. Thank you.
It's all part of the fun of development.
I found I had this problem before, and I just removed the never allow rule from the not from my device, but from the original rule. I mean, this is probably not the best way to do it. If there is a never allow rule somewhere, it means that needs to be there. But on some embedded device, you need to allow accessing, for example, some low-level stuff. If you don't want to, there is for sure there are better ways to do this. For example, creating some custom services and so on. So you do the right things. But a quicker way to access some kind of specific device, for example, to allow to some specific application to access this kind of devices.
Yes, so I would class that as cheating, somewhat. But it kind of comes down to whether you need to pass the various CTS and BTS tests. Because
exactly.
they will throw errors if you do try to run the CTS. If your device is not being certified, so it's for a closed market or a closed group of users, and assuming you have assessed the security implications of changing that code, then sure, that's fine. It's exactly the same how we do it with any other embedded operating system.
Well, I think that these never allow rules exist also to add some extra security. I got also this problem when I was trying to have a different file name for the real daemon. So, and that would break one of the never allow rules that exists only a real daemon that communicates with the framework. So in case you remove that rule, then basically in case a hacker gets access to the system, it can create their own real daemon that communicates with the framework and then overrides the access to the messages, to the SMS, to the calls, etc. So that's why also the never allow rules exist in the framework.
Yes, exactly so. Yes, yeah. But they are, as I think Andreas was saying, they are. The policy that is in AOSP is kind of oriented towards mostly the smartphone use cases. And there may be use cases where you need to access particular hardware where a never allow rule doesn't quite make sense. Also, sometimes they are a little bit over zealous sometimes. So in Android 10, I seem to remember there is a never allow rule which prevents a HAL audio daemon from accessing any kind of network socket. which is perfectly fine if you're looking at a phone or something. But when it comes to the automotive use case, quite likely the audio HAL is going to be using sockets, because typically the audio is distributed via Ethernet. So I think you have to balance things. I wouldn't change a never allow rule without a very good reason. And of course, I'd only be able to do that if I don't need to pass the various tests.
Okay, thank you.